Okay. So in this question, we have a mercury manometer, and we need to measure pressure in the pipe, which is here. And we will need to find it in PSI and also in inches. And we have a manometer reading of H of 3 feet, which is here. So in this question, we have two different sections. The first one is here, and the other one will be here. And also, as you know, at the same elevation, we have same pressures because these are both mercury. So we will need to calculate pressure over these points. So if we start from left-hand side, hydrostatic pressure is gamma and H. So on the left-hand side, we have 3 feet times specific weight of mercury. And on the right-hand side, we have pressure in the pipe plus this 2 feet of pressure. With another specific weight. So in the question, I think it's not given, but to find the specific weight of mercury, we need to do specific gravity times the specific weight of water, which is 13.6 times 62.3. So this will give us 30 feet times which is equal to P plus 2 feet times 62.3 pound per cubic feet. And from there, we can calculate pressure as an integration. We are asked to find in PSI and also in inches. So to find in PSI, it will be 16.8 PSI because we found in feet and we just converted to PSI. And we also need to find in inch. So from the hydrostatic pressure equation, the H pressure height is pressure over specific weight of mercury. So basically, it will be which gives feet. So we found that the pressure is 2,420. And the specific weight of mercury is, from that we can get 2.86 feet or 34.3 inch. So we found both of these results. And do you have any questions here? Okay. And also, for the upcoming questions, I will directly write calculations because it will take some time to calculate everything. So I just give values and you can do calculations by yourselves. And first, I want to ask if everyone is familiar with Moody diagram. Great. Okay, now in this question, we have a commercial steel pipe, which is horizontal, which is important for the question. We have diameter, which is D, and we have flow rate 3.5. The temperature is 20 Celsius. We need to calculate the pressure drop in the pipe per kilometer, and we are ignoring minor losses. So here we have pressure drop equation as specific weight times net loss. Actually, I can write it HF. Here, HF is frictional loss throughout the pipe. And since we ignore minor losses, we will be only calculating that frictional loss. So let me first start with the equation of frictional loss. Here we have F, which is friction factor. We have length, velocity, and we have acceleration and diameter. And let's first start with what we know about this equation. First of all, we know diameter. Of course, we know acceleration. We know length because it is given as 1 kilometer. We know velocity as well, but of course, we will calculate it now. And the only unknown is friction factor, which requires us to use Moody diagram. And for Moody diagram, we need two variables, which is Reynolds number, and the other one is E over D, which is roughness over diameter of the pipe. And in the question, the roughness of the pipe is not given, but we can find it from tables, so I will directly write it as well. And from that, we can calculate E over D. Here, the important part is the roughness is in millimeters, but the diameter is in meters. So don't mix these up. They will need to be in the same unit. So we can write 1500 millimeters, which will give us 0.00003. And on the other hand, we can calculate the Reynolds number as well. But for that, we need velocity first. So from the continuity equation, we can calculate it with this formula, which is 1.898. Okay, yeah. Now we are just going to use this velocity in Reynolds number here. So it will be 1.5 times velocity. And here, kinematic, because it is also not given, but it is given in tables, so it is this value. Actually, let me move this. And for the Reynolds number, we can get 2.87 times 10 to the power of 6. And now we have everything to find friction factor from the Moody diagram. And we are coming up here. So we have almost 3 times 10 to the power of 6 Reynolds numbers, which will be around here. And we will also have a 0.003, sorry, 0.00003. So it should be around here, I guess. Yes. You can see it's here. So we are going to draw a curve. And then we are going to intersect these two lines. And then draw a straight line, which will be here. From here, we can get something like 0.011. This doesn't have to be perfectly same, but even closer results are okay. So the first friction factor is 0.011. And now if we check the head loss equation, we found everything we need. The head loss will be 0.011 times the length was 1 kilometer, which is 1,000 meters. We found the velocity. And diameter is 1.5 meters. Here we can get head loss as 1.47 meters. But we are asked to find pressure drop, which is delta P equal to head loss times specific weight. From here, if you do the calculations, you will get in kilopascal. Okay, is there any question here?
Could you repeat where you got is that 9,790?
Okay, so here we have a specific weight of water. It is this value if it is international units, or if it is British, it will be, or you can use it as kilonewton per cubic meter. Is that clear?
Yeah, yeah.
Okay, great. So, okay, now in this question, it's also pretty similar. This time, we need to find flow rate of water at 20 Celsius degree. At this time, we are given the pressure drop. We have the length of pipe, again, which is horizontal, and we are given the type of pipe, which is cast iron with 60 centimeters diameter. And again, we ignore minor losses. And if you refer to the previous question, pressure drop was loss times specific weight. And we can keep this here. Okay, so for this kind of questions, or actually for many of these questions, we can use energy equation because it contains pressure, velocity, elevation, specific weight. So it has everything we need. So we can use energy equation between 2 points, and then we can get whatever we need. So let me write it here. Here we have pressure height, velocity height, and elevation. On the other hand, so on the other side, but this time we have head loss. So we can imagine this something like this. If it is a pipe, it's point A, this is point B, and we consider the movement of water from point A to point B. Therefore, head loss will be on the right hand side here. Okay, and do this. Okay, the most fun part in this question is eliminating some values. So, do you want to say which one we need to eliminate based on the horizontal pipe or elevation or anything? So, let me help you. So, first of all, the pipe is horizontal, which means we have the same elevation, so that we can directly eliminate these two variables. Uh, another thing is this is a pipe, so and there is no change in diameter, which is always constant throughout this pipe, of course. So if we have velocity here, it will be same here as well. So that in this equation, we can eliminate these velocities as well. However, this doesn't mean that we completely ignore velocities. Of course, we will calculate velocity, but they will be same. So we will not need that in the equation. Okay, since we are given the pressure drop, we can find something from there. So if we leave head loss alone, it will be delta P over specific weight, which means PA minus PB over specific weight. So actually, as you can see, it is same here. So this is not a fancy equation. It's just coming from this energy equation. And from there, the pressure drop was 17,050 Newton over square meter. So this is actually PA minus PB. And on the down, we have specific weight again, which is almost 10,000 Newton per cubic meter. As you can see here, it will give a value in meters, which is 1.76 meters. And now we need to find flow rate, and we wrote the equations we need. But since we don't know velocity now, we can use head loss equation because we have already found that here. So if we write it, if we think about what we know length, we know acceleration, we know diameter, and we don't know F, and sorry, we don't know F and the velocity. So from here, if you write everything we have 1.76 and length is 350 meters times v square. Here again, we need to use Moody diagram because we don't know the friction factor. And for Moody diagram, we need Reynolds number and E over D. Again, we of course know E over D, but we don't know the Reynolds numbers. So that here we need to assume a number for the friction factor. So, for example, we can start with a number like 0.017. Here we have to do this assumption because we don't know F and we don't know velocity, so that we are giving a value to one of them, and then using Moody diagram, we will see if it is correct or if you need to change the friction factor as well. And since we assumed F is 0.017, we can use this in the equation here. And from this equation, since the only unknown is velocity, the velocity will be 1.87 meter per second. And now, of course, this is coming from assumption. And now we need to check if V is correct. Actually, velocity and friction factor, if they are correct. So we will calculate the Reynolds number using this velocity. Reynolds number will be 1.87 times diameter. And again, we have kinematic viscosity, which you can find from tables. And here we have this amount of Reynolds number. And we can also get E over D. Here, this value is coming from the property of the pipe, which is roughness, which is 0.26 millimeters. And we have diameter as 6 centimeters, which is 600 millimeters. So from here, we can get E over D as 0.0004. And now that we have these two variables, we can go to check a Moody diagram if the assumption is correct. So we are visiting Moody again. Okay, we have 1.1 times 10 to the power of 6. Oh, it will be something like here. It's right here. And on the right hand side, we have E over D, which is 0.0004. It should be around here. Again, we are going to draw a curve. We are intersecting these two lines. And again, a straight line. And I will stick with the assumption, I will stick with the solution of the question. So this may be 0.016 or 0.017, but let's say this is 0.017. So from here, we can see that our assumption is correct because when we use that friction factor, we calculated velocity. From that velocity, we calculated Reynolds number. Using this Reynolds number, we again calculated friction factor as 0.017, which is the same. But for example, if it wasn't 0.017 and let's say 0.02, we were going to use this friction factor in head loss equation. And from that, we will get velocity again and Reynolds number again. And from we will come here again and find friction factor. So it's a basically iteration. Yes. So from here, and assumption is correct. And usually starting with an assumption of like 0.02 is usually good because based on my experience, it usually comes around this value. So it is wise to start with that value. So since we found the friction factor, and the velocity was 1.87 meter per second, we can easily calculate the flow rate, which is Q is equal to velocity times area. Diameter was 0.6. Okay, do you have any questions here? And let me know if I'm going too fast or too slow, so I can adjust myself. Okay, in the question 4, we have something different. But, I think this is also pretty easy. So let me start with the reading of question. We have 3.5 feet diameter, and we are given the commercial steel pipe. And we have the temperature. So it says the water flows from reservoir A to B. As you can see here. And the pipeline is 2.5 miles. The elevation difference between reservoirs is 395 meters. So with this surface and this surface, we have 395 feet of elevation. Or we can say HA minus HB is equal to 95 feet. And actually, they calculated discharge using the Darcy-Weisbach equation as 181. But now we need to find discharge again. But this time we will need to use Hazen-Williams equation and the Mannich equation. And we are ignoring minor losses again. And of course, we are not ignoring minor losses every time, but I think in next question we will start considering minor losses as well. So since there is no minor loss here, we only have frictional loss or loss through the pipe. But if we had minor losses, we were going to have something here, enters the pipe or leaving the pipe. Or maybe we could have some valve here or some elbows like this. As always, start with energy equation between these 2 points. And of course, have those at this site. Okay. We can again eliminate something here. And do you have any guess which one would be?
Would it be pressure?
Yes, great. And we are going to ignore pressures because they are both open the atmosphere. And we have something more.
Velocity?
Yes, correct. So I like this kind of quizzes because you just eliminate everything. We eliminated pressure because they are both atmospheric pressures. And we also eliminate velocities. And it is mainly because assume that these are reservoirs, and since they are very large, and we are considering the velocity at this surface, there will be just some minor velocity here. I mean, there will be no flow or movement, significant movement, of course. So that since it is very close to zero, we can ignore velocities at these surfaces. So that here we only have a loss which is equal to h1 minus h2, which was 3,895 feet. Which is head loss. So in the question, let me add a page. In the question, we need to find discharge using Hazen-Williams. So we are going to use this equation. And since we are using this unit, we will stick with this equation. And here you can see head loss. Head loss is equal to K times Q over M. So K will be coming from here. M will be coming from here. And we already have head loss. So we can calculate discharge easily. According to Hazen-Williams, K is D over D over 1.85. This C is coming from coefficient. I'm not sure if it is given in the question. In exam or in quizzes, it should be given to you. So from there, 4.73 times the length, which is 2.5 miles. The diameter is 3.5 feet times C over 1.85. So from here, we can get K as 0.0132, and head loss was equal to K times Q or M. It will be equal to Q to the power of 1.85, and the head loss was 395 feet. And this gives Q as 263 cubic feet over a second. And for the monies, we are going to do exactly the same things, but with different equation, of course. And here we will need to use this M value and this equation. K value for money is and here N is roughness coefficient. And again, yeah, we don't need to find this equation because it's a feature of the pipe. And it is given as 0.01. It is 2.5, and there is 0.5. Come here, the K is 0.00771. And using the similar same equation, which gives 395 is equal to 0.00771 times Q over Q of 2. And here Q is equal to 26 CFS or cubic feet per second. And now we can see the difference between these different equations. For Hayes and Williams, it was 263, and for Mannix, it is found as 226. Is that clear? Do you have any questions? Okay, so if everyone is fine, we are going to question 5. Here we have another pipe question. So the diameter is given as 4 centimeters in a wrought iron. The important thing is it's horizontal pipeline from point A to point B. The length is 50 meters. And now we can see the minor losses, a valve and 2 elbows. And we have this value. And if you check your textbooks, you will find corresponding loss coefficients for these losses. And the pressure at B is given as 192. The flow rate is given here. And we just need to find pressure at point A. So let me draw the pipeline. So we have B, we have A, and we know the pressure at P, sorry, at B here. And again, we are going to start with the energy equation. So we will do something similar, I think, in question 3. Since this is horizontal, we are just ignoring elevations here. And also, since there's no change in diameter, the flow rate will be same throughout the pipe. I mean, from A to B. So that the values will be the same. So we can also eliminate these values. And let me clear this equation. If we move pressure at B to the left-hand side, the loss will be this one, which you're already familiar. This time we will have 2 different losses, which is a major or friction loss and minor loss. This is too hard pipe. This is only for valves or elbows, gates. Okay, so to calculate losses, we need to find velocity because final loss is sum of all of loss coefficients times v square over g. Major loss is, of course, this equation. So anyway, we will need the find velocity. So since the flow rate is given, we can calculate velocity as q over a. So yeah, you need to be careful about line meters. It is given as 4 centimeters, but here we use it as meters. From here, we can get velocity as 4.77 meter per second. Now, to get the question in general, what we know and what we don't know, is we need to find the pressure at point A. We definitely need to know the head loss. And to know the head loss, we need to calculate this one and this one, of course. So we know the loss coefficients, we know velocity. The only unknown is, again, friction factor. And we know the length. Okay. So to find F, use Moody. And Reynolds numbers we will need to calculate. And I'm directly writing the result because we did that many times. And for E over D, it is given as 0.045 millimeters per 40 millimeters, which gives 0.0113. And now we will visit smooth diagram again. So we have 2 times 10 to the power of 5 and 0.01. Okay, so Reynolds number is around here. Not exactly 2, but it's very close to 2. And for the E over D, we have 0.001. So it should be around here. And now again, we are drawing the curve. And we are drawing this straight line from Reynolds numbers. Intersection is here. So again, I will stick with the solution of the equation. So it may be 0.023 or 0.022. But let's take 0.022. And now it's time to calculate all of these head losses. which will be the minor loss and also these major loss. So I can do something like this. Since the velocity height, the velocity height, which is v square over 2g is common for both of these losses, we can do sum of those coefficients plus f l over d. Let's keep writing. And from textbook, those coefficients are given as for gate 0.15 and for elbows 0.17. So we have one valve, which is 0.15 and two elbows. Plus the major loss, which will be 0.022 times 50 over 0.04. And this will give us the total head loss. I think I didn't write the exact number here. Okay. So we will use this equation eventually. PA over PA over specific weight is equal PB over specific weight times head loss, and PB over specific weight was just a second. Yes, 92. It is in kilopascal, but we will write it in Pascal because kilopascal is kilonewton square meters, and if you write it in Pascal, it will be Newton over square meter. So this is just to provide consistency between units. And the specific weight for the water is again Newton over cubic meter plus head loss. And from here, the head loss will be coming from here. And the pressure at point A is equal to 510,000 Pascal. Is everything clear here? And I also shared these notes after the class. So don't worry about if you miss something. Okay, since everyone is fine, I'm going to next question. Okay, here It is also similar to question 4. Yes. But this time we have open atmosphere here at this at point 2. And another difference is we have oil flowing. We are given to discharge our flow rate. We have a pressure tank here, and it pushes the oil through this 200 meters pipe with 15 centimeter diameter. And we have the type of the pipe. And the surface of the fluid and elevation at 100 meters. The elevation here is 100 meters. And at the end of the pipe, the elevation is 106 meters, which is here. And we need to find the air pressures that we will need to push this fluid through the point 2. So since this is a pressure tank, it will apply some pressures and it will help water to move from point 1 to point 2. And we just need to find this pressure. And we will get started with an education again. And as always, we will keep going by eliminating some values. So first of all, since this is a very large tank and we are considering the velocity at the surface, it should be very slow that we can neglect so that it is 0. But of course, we cannot remove pressure because we need to find that pressure. And this time we will also have velocity at this point because if you think about that, we will push the fluid here and it will go out with some velocity and with some flow rate so that we need to keep it here. But we can again discard the pressure because it is open to atmosphere. And here we have elevation of point 2 as 106 meters and for point 1 is 100 meters. And let me clean the equation again. Since we need to find the pressure at point 1, I'm leaving it alone. And let's move this h to here, which will be 6 meters plus net loss. And in the question, it is not stated that we can ignore minor losses, so that we will consider minor losses as well. So here, when we say head loss, we will have frictional loss and minor loss. And this was, of course, this equation. For minor loss, it is K square over 2. Here, the K is the loss coefficient at this point, which is close to pipe. So here, again, from the textbook, K is 0.5. And it is usually 0.5, so you can directly use it. And again, let's check what we have here. Do we know the velocity? Of course, because we know this flow rate, we know acceleration, we know diameter, we know length, and we need to find friction factor again. And to do that, of course, we need to find Reynolds number and E over D as always. And in the Reynolds numbers, we have velocity term. So I will first calculate velocity as Q over A. And we have flow rate, and the diameter was 15 centimeters. So that we can convert it to meters. Which will be 0.668. And now we can calculate Reynolds numbers. Diameter was 0.15 meters. And we have kinematic viscosity. This is also a property of the fluid. And I think it was given in the question. Yes. And on the other hand, we have E over D. And this time, you can see the value of the roughness. And again, be careful about the unit because it is given as meter. And I will directly use diameter as meter here. And again, we need to visit with the diagram.
Wouldn't it be 0.15 again for the diameter?
For what?
For the diameter in the E over D, wouldn't it be 0.15?
Yes. Correct. Yes. Thank you. Good catch. And the Reynolds number is now we are going up again for the moody. And we have 5 times 10 to the power of 4, which should be around here. And on the right hand side, we have 0.008. It should be not here, I guess. So we have E already here, and we have Reynolds here. And draw the curve. And again, if you stick with the question, it will be 0.0024. And from that, we can calculate the head losses. So we just need to use this equation actually. So let me open another page and copy this equation. Okay. Okay. I finally got rid of the link. And let me write everything here. The velocity was 0.679. 6 plus head loss. And total head loss is, again, we can use v square over tg, 2g, and k plus fl over d, which gives us k was 0.5 and f is 0.024 times length is that over diameter was. Okay, from there you can calculate P1 as 0. So P1 over specified as 6.79 meters. But we need to find the pressure so that we will just multiply these two values. P1 is equal to 6.79 times of oil. And to find that, we need to use specific gravity of oil times specific weight of water. This was given as 0.84. And again, the specific weight of water in SI units. And finally, this gives 55.8 kilopascal. Okay, is everyone clear here? Okay, great. So if you're okay, I'm going to the next question. And I'm also recording the video, and I will share everything, probably using the YouTube link, so that you can watch it again if you want. Okay. So in this question, we have parallel pipes. Parallel pipe here, and the other one is here. And we have diameter of pipes AB, which is here, And we have a diameter for CF, which is here. And these are 2 meters or what? And thus the Weisbach friction factor is 0.02 for these two pipes. And we have the length of AB and also CF. So length is here 1000 meters and here 900 meters. And we also have the discharge in pipe AB as 60, which is given here. And now we can consider parallel pipes. The length of the branch one is 1000 meters, which is this one. And its diameter is 2 meters. And friction factor is 0.08. And for the branch two, which is here, we have a length of 800 meters and a diameter of 3 meters, and a friction factor of 0.02. And here it says that a discharge of 20 cubic meter per second is added to the flow at point B, which is here. So we have an inflow at this point. And also 10 cubic meter per second is taken at point C. And so we have outflow here. So once we are coming to the point B, we will have both of these discharges. But after this pipe, we will lose 10 cubic meter per second, and we will continue with 70 cubic meter per second. Because we have 60, 20, and we have 80 here, and the remaining is 70. Okay, so in the question, first of all, we need to find the head loss due to friction between section A and F. So the total head loss, we don't have minor losses here. And secondly, we need to find the discharge in each of these branches, which is branch 1 and branch 2. Okay, let me get started with the first question. So we need to find the total head loss due to friction, so that we will have head loss 1 here, head loss 1, head loss 2 here, head loss 3 here, head loss 4 here. So here's my question. Are these same or not? This head loss at branch 1 and 2. Who can tell this? Or let me know what you think. Okay, I'm explaining that. So since these are parallel pipes, let's assume that we have a pressure here and we have another pressure here. So the pressure drop will be same regardless of the path. So even if we go from this way, if we choose this way, we will have the same pressure drop. Or if we go from here to this point, again, we will have the same pressure drop or same head loss. So it is important to know that for parallel pipes, head loss 1 is equal to head loss 2. This will help you to solve questions because without knowing that information, um, it may be very impossible to solve that. So knowing that, we can move forward. So in this question, instead of using two parallel pipes, we can consider creating a single pipe, which is equivalent to these two pipes. So let's write it here, equivalent single pipe instead of two pipes. So here we are going to uh, benefit from this table, which is equivalent pipe equations, which you can find in your textbook. Here we have that's the Weisbach equation, and if it is series, if it's pipes in series, we were going to use that one. But since we are talking about parallel pipes, we are going to use this equation because we have we have this Weisbach friction factor as stated in the question. So we will stick to this one. So this is how it works. Equivalent diameter, equivalent friction factor, and equivalent length is equal to diameter for branch 1, friction factor of branch 1, and length of branch 1 plus same for the second branch. Here we already know all of these values because they are given in the question. So here we need to find LE, which is equivalent pipe length. And to do that, we will assume some values for DE and FE. Here you can choose whatever you want, but of course they should be not crazy values like choosing diameter, like 20 meters. This would be crazy, but you can pick something similar to other pipes. And we have other pipes as 3 meters. So we can stick to this one. And for the friction factor, again, we can select this 0.02 as the equivalent friction factor. This will not affect the result so much because based on this DE and FE, we will get length of the equivalent pipe. So if you write everything here, for the branch 2, And from here, the only unknown is length of equivalent pipe, which you can get 4 meters. And now, since we know that, we can calculate the total head loss. As HL1, HL A to B plus HL B to C plus HL C to F. Okay, it should let me move it speech. So from A to B, we have where's the question? Okay. I forgot to add equation here. But we have an equation which is for head loss 0.0 times F times L over D over 5 times Q M. This is for one inch. So using this equation, we can calculate the head loss in the pipe AB. So the discharge at point AB is 60 cubic meter per second. And here, since we are dealing with Q to the power of M, and M was 2 for Mannings, so we can write this equation plus now for the BC, which is either here or here, because we already have an equivalent pipe, so we will directly use that. Friction factor 0.02, and we are using the length that we found here. And this time we have 80 cubic meter per second discharge, because we have 60, we have 20, and it will be 80 at this pipe. And finally, we can calculate the head loss from C to F. Similarly, length is meters and diameter is 3. And this time the discharge was 70. Because we had 80, we lost 10. The remaining is 70. And let me directly write the results values. So we need to find total head loss, which will be coming from the equations. And again, using the same equation, I mean this one. Okay, and now we found the total head loss, and now we need to find the discharge for each branch of these two parallel pipes. So head loss 1 is equal to head loss 2, which will be 19.3. Which is equal to 0. And let's find friction factor for branch 1. Yes, they are 0.018 and 0.02. And of course, this is equal to Q1 over 2. Similarly, head loss 2 was equal to head loss 1. And this time we have friction factor as 0.02. And now this helps us to find the discharge. And from these equations, the discharge in branch 1 is 20.4 cubic meter per second. For Q2, 59.2 cubic meter per second. Okay. Is there any question here? If not, this was the latest question for this session. So then I'm stopping the